Okay, let's wait for 2 more minutes to start today's class. Okay, let's start today's class. Today we will continue talks about continuous time convolution integral. Actually, we talk about the two different convolution signals. Yeah, one is for dt time, discrete time convolution sum, and one is continuous time convolution integral. And we haven't finished the CT convolution integral. Today we will continue talking about that. And this is today's goal. Firstly, let's try to review the convolution sum for DT-LIT systems. And then we will review the convolution integral for CT-LIT system. And finally, we will compute the convolution integral for CT-LIT system analytically and graphically. And actually, before we start this class, I want you to think about one question. And why we want to learn the LIT system for now? Like why we want to talk about the convolution sum and convolution integral? And if you notice that, and we just talk about how to get the output yn or yt, am I right? Actually, for a system, usually if you want to use mathematical form to represent this system, sometimes your input signal, am I right? And the impulse response, actually you can easily get it because if your input signal is a delta signal, like it's a impulse response, impulse impulse function, and your output should be impulse response, and you can easily get that. Since you can easily get your you can easily define your input signals and your input response signal, you can use input signals and like response, impulse response signals, and to represent the whole system. Am I right? The yn equal the like input signals convolution with impulse response, or it's just like a system. You can use mathematical form to represent this system, and then you can try to analyze this system. Yeah. So that's the reason why this system, this one is very important. Okay, let's continue. Let's try to review the DT LIT systems. And firstly, let's try to like think about how can we get the mathematical form to represent IIT system. Yeah, firstly we use sampling property. Yeah, and the xn like multiple delta n equal x0 multiple delta n. This is sampling properties we have already talked about. Based on the sampling properties, we have this equation, and you can see this delta like this impulse function is very important for our signals and systems. It can help us to deal with the signals. Yeah, and then we have this equation. Based on these equations, actually we can use this like convolution form to represent our input like input signals, and based on this input signals form, and yeah, this is we call it DT shifting property. And based on this, and we also know like if the impulse like function goes through the system, we can get impulse response, and then from this the input signals and the impulse response, and we can get the since this system is we always talk about LIT systems in this chapter, so we can get this equation. Yeah, we can get this equation, and this equation like we also call it what? Convolution. Yeah, convolution form. And then we use what symbol to represent it? Yeah, the star. Okay, yeah, we can use this star to like to represent the convolution, which means the output should equal like input signal convolution with impulse response. And also we can use one convolution property. What convolution property we use here? It is like what's that? Yeah, commutative. Yeah, commutative property. Yeah, and then we call this convolution sum. Yeah, because you can see there is a summation symbol. That's the reason why we call it convolution sum. And then yeah, this is how can we like get the output based on the input. And then from the definition for the like LIT system, and we have this one, we have this property. Yeah, like this will, what's the property name for this one? Yeah, it is a shifting property. Yeah, and this property actually is it's very useful for us to simplify our computation. Yeah, and then let's talk about the convolution sum. Actually, for the DT LIT system, and we usually want to get the output, like use the mathematical form to represent the LIT system. Actually, usually like we know like the convolution sum can help us to get the output. Am I right? So like actually the convolution sum can be computed analytically in two cases. The first one, like the xn and hn are given as short impulse sequences, and yeah, this one, if like xn and hn are given as short impulse sequences, we can use some properties. Yeah, here it's just a show like a shifty property and a distributive property. Also, you can also use a associative property and a commutative property. Yeah, we use those properties help us to simplify the Sn convolution with Hn and then get the final output. Yeah, this is case 1. And for the case 2, and when the Xn and Hn are defined with a closed form, the key is to convert the convolution sum into the geometric series sum as this thing. Yeah, which if your like convolution sum can be converted to this form, and then you can use this equation. And if your like convolution sum can be converted to this form, and then you can use this equation. Actually, we talked about those two before. And what's the difference between those two? Yeah, you can see one like is just from like n naught to positive infinite, and the other from n naught to n1. Yeah, and like based on the different situation, we will use different equations. Actually, we have already talked about like several examples for those two cases, and also for the case 2, those different situations. If you have any question, just let me know. Okay, and then let's continue. Let's try to talk about the CT-LIT system. This is what we talk about last class. And for the CT-LIT system, actually it's very similar with the DT-LIT system. Yeah, the first thing, we from sampling property, yeah, and then we get this equation. And then from this equation, we can represent the like input signals using this equation. Actually, this is also kind of like convolution form. Yeah, and from these input signals, yeah, this is we call it a CT shifting property, and we also we also can easily get impulse response. And from the input response and the input signals, we can use this equation to represent the output. Yeah, you can see. Did you notice the difference between the CT-LIT system and the DT-LIT system? Actually, you can see here is a summation and here is integral. Do you know why? Yeah, I think some students might know, like because for the DT, the term is like integer. Yeah, so it is, you don't need to use integral. But for the like CT signals, it is, the term is like is now integer. Is any value between those in this range. So you need to like use the limitation content. So you need to use integral. You need to use integral like a symbol. Sorry. Here. Yeah. And then actually, yeah, this equation also we call it a convolution form. So we can use this form to represent this equation. And then, yeah, here we also use commutative property, and we call it a convolution integral. Yeah, you can see the difference between this one and this one. This is convolution sum because there is a summation symbol, and here is a convolution integral because it is integral. Okay, and for the CT-LIT system, we also have this property, shifting property. Yeah, and you can see if you can like if you try to get your output, and your output like include this atom or similar to this atom, and you can use this shifting property. Yeah, it is very useful. And okay, let's try to sum the like summary the convolution integral. Yeah, the convolution sum actually can be computed analytically according to the following two cases. The first one is like xt or ht are given as impulse sequences, yeah, like this. And then we can use some properties, like this is shifting property and a distributive property, like a commutative property or like associative property to simplify your output and get the proper form to represent your output. And then case 2, like is when xt or ht are given in terms of this form, and then we can use we can use this equation, yeah, because you can see why we use this equation, because from the definition, your output should should like have this form, am I right? And there will be an integral, and then your final result will be similar like this form, and then you will use this equation. Actually, this equation we talk about in the beginning of this class, and then we have this equation, and the key here, the key is to remove the unit step function, u function. Yeah, by changing the boundaries of integration to make the integration computable. Yeah, this is what we need to do. Okay, and then this is a convolution integral and a convolution sum, and we will continue to talk about convolution integral. Before we talk about that, let's try to review convolution properties. Actually, what properties we have already learned? Do you remember? Yeah, there are 4. Yeah, the first one is shifting property. Yeah, the shifting property, which means if your like input like a convolution with yeah, actually we also when we talk about the system and signals in the chapter 1, we talk about the shifting, but just pay attention. We don't involve convolution there. I'm right. Yeah, here we have convolution. Yeah, if you have convolution symbol, then you have this equation. Otherwise, you don't have this equation. Just pay attention to that. Yeah. So you have this one, and similar for the CT signals. Yeah, you have this one, and the second one. Do you remember? Yeah, it is a commutative property. Yeah, commutative property. I think it is easy to understand, which means you can change the order. Yeah, xn convolution with hn equal hn convolution with xn. Similar with CT signals, xt convolution with ht equal ht convolution with xt. Okay, and then for the distributive property, which means if there is a path list, yeah, and you can remove this path list, and then it will equal this form. Am I right? Yeah, just put the kind of like similar like a multiple. Yeah, but it is convolution. And for the like CT signal, it is similar equation. Yeah, just try to remove the path list. Yeah, we call it a distributive property. And the last one is associative property. Uh, yeah, which means, sorry, I think I just put this wrong. Yeah, just remove, just forgot this one. And this one, yeah, X convolution with H1N, like convolution with HN, which means the order can be changed. You can like convolution XN with H2 firstly. You also can like use XN convolution with H1, then H2. Yeah, it's a similar thing. Yeah, here, this one, I just want to put the like CT signals. Yeah, like XT convolution with H1T convolution with H2T equal XT convolution with H2T convolution with H1T. Yeah, so I will change it later. Yeah, if you have any questions, just let me know. So actually, those convolution properties are very important for us. Do you know why? Yeah, it can simplify our computation for the output. Yeah, let's try to review example. Yeah, this is actually this example we talk about in last class. Yeah, this is our, what's the name for this? Yeah, impulse response. Yeah, it equal this one. And this is our input signal. Yeah, which means if HT convolution with ST will equal this one, because this equal this one. This is just a HT and this is HT. Am I right? And then equal this one. What property do we use here? Yeah, you're right. Shifting property. Okay. And then what's this one? This is just a XT, like a right shift to the right. Am I right? Right shifted with T now. So it's just like this. And this one is just like the X, like the original one, left shift T now. So it's this one. But we talk about that in the last class. We don't like these two parts overlap. Yeah, because it is now, it will now follow the LIT system again, we will now follows a LIT system property. So we don't like it overlap. So there will be, this is just, there will be a condition like without overlap. If it is without overlap, which means this point should greater than this point. That makes sense to you? So we have this equation. And then our T naught, T naught should, 2 T naught should greater or equal 2, and T naught should greater or equal 1. Am I right? Yeah. Any question? Okay, no question. Okay, and then this is the other like signals. This is our HT, and this is our signals. And similar with this one, firstly we just right shift and then left shift, but we don't like overlap. So which means the T naught should greater equal negative. Here is negative T naught plus 1. I'm right. So and then our T naught should greater equal than 0.5. Yeah, this is what we will have for this example. Any questions? Okay, and okay, let's talk about the other question. Let xt be the input to a LIT system with unit impulse ht, where like I have already given you what is our input signals and what is impulse response. Here, like the impulse response is what? Yeah, unit step function. Yeah, which means it just looks like this. This is our ht. And what is our xt? Oh, sorry. Yeah, our xt should similar like this. So what is output? What is output? Yeah, I think the equation should pop up in your mind. Okay, it is convolution. Yeah, convolution integral. So we use this equation, and then we put x tau ht minus tau in this equation. Am I right? And then we have this one. Okay, what's the next step? Actually, we talk about that when we discuss the convolution integral. The key is to remove the unit step function. Am I right? So here we try to remove unit step function. Yeah, firstly, let's try to remove t tau. Let's try to remove unit this atom. If we want to use this atom, what does that mean? Which means the tau should, if the tau smaller than 0, which means this atom will 0. Am I right? So it will disappear. If the tau greater or equal than 0, which means this one will be 1, it can be removed, but it will be there. The equation should be there. We can get this equation. I'm right, because if tau greater or equal than 0, and then this one should be 1. So we just remove this one, and otherwise it will be 0. We don't need to write it down here. I'm right. And then let's talk about this one. If we want to remove this one, which means we should let t minus tau greater or equal than 0. I'm right. Yeah, because if this t minus tau greater or equal than 0, which means this atom with this part will be 1. Otherwise, it will be 0. Yeah, we don't need to pay attention to that part. Am I right? So which means the tau should smaller equal than t. Am I right? Yeah, we talk about in this situation like tau should greater or equal than 0, and here t should smaller equal than t. So we can here. So we can have this equation. The tau should from 0 to t, and then we have this equation. Am I right? And here t should greater than 0. Otherwise, this equation does not work. Okay, then we have this equation. We talk about this now, just now, and we have this equation. Then we can use this equation. What is a here? It is 0. Am I right? What is b here? It is t. So then we can use this equation. Easy to get this one. That makes sense to you? So then this is our yt. Easy to get that. Am I right? Yeah. And here I just add ut. Why? Do you know why? What is ut? This is ut. Am I right? Am I right? So which means we move t greater than 0, because ut, which means if t greater than 0, this is 1. If t smaller than 0, it will be 0. I'm right. So this one, this like yt should 0. So this one is just replace this condition. That makes sense to you? Okay, let's continue. Yeah, this is our final output. Yeah. Okay, let's talk about the other one. Yeah, this one, like I gave you the input signals, and also I gave you the input response. And what is, yeah, this is the input signals, and this is the input, like response, impulse response. Okay, what's YT? Yeah, the first thing pop up in your mind is just the convolution, am I right? So you use this equation, and then put x t here, ht here. But when you put this 2 here, just pay attention. You need to replace t with tau. Replace this t with t minus tau. Am I right? So your equation should equal like this. Yeah, you replace t with tau. There are 2 tau, u negative tau, and you replace t with t minus tau. You can get this one. That makes sense to you? Yeah, just pay attention to that. When you like resolve the similar questions, don't forget these things. Okay, and then we talk about this one. Yeah. Our equation should, our equation should become this one. Do you know why? Do you know why? Yeah, if you notice the difference between this one and this one, you will find this atom disappear. Am I right? So which means what is U negative tau? Which means negative, if negative tau greater equal than 0, and this atom will be like 1, am I right? So which means tau should smaller equal than 0, am I right? So this atom will be 1, otherwise it will be 0. So then this is why this equation works, because here this is tau's like range. It should smaller equal than 0, and then this atom will be removed. That makes sense to you? Okay, for this atom, what should we do? We should let t minus tau minus 3 greater equal than 0, and then this atom should be 1, otherwise it will be 0. That makes sense to you? So our tau should smaller, like equal than t minus 3. Here we have, this is the other upper boundary, am I right? Let me try to make this clear. Okay. Yeah, which means for this situation, we have one upper boundary, and then we have the other upper boundary here. Am I right? So this leads to the second upper boundary, and we need to consider 2 cases similar with the situations we met in the like DT convolution sum. Here, which means there are 2 different upper boundary. We need to talk about 0 and t minus 3. Which one is like bigger? Which one is smaller? If t minus 3 smaller equal than 0, what is upper boundary? You know what is upper boundary? Yeah, the upper boundary should become t minus 3. Do you know why? Yeah, because if this one is the smaller upper boundary, which means if my upper boundary is t minus 3, which can make this is 1, also makes this is 1. Am I right? Yeah, so your equation should become this one. And then you can use the equation, like this equation, to easily to get the final result here. And then let's talk about, yeah, this is t smaller equal than 3. And then let's talk about the other situation, t minus 3 greater than 0, which means the smaller upper boundary is 0. Am I right? Which means if then our upper boundary should 0, and we have this equation to get this one. And this is our like YT, finally like output. Okay, let me do a sum, which means if you have 2 different upper boundary, you need to choose the smaller one as your upper boundary, which means this upper boundary should satisfy this one and also satisfy this one. Also works for the convolution sum. Yeah, if you have two different upper boundary, you need to choose the smaller one as your upper boundary. If you have two different like a lower boundary, you need to choose a bigger one as your upper bound, lower boundary. Sorry, remember? Yeah, this is you need to pay attention to. Okay, and let's talk about some other examples. Yeah. Okay, this is a homework, and let's talk about how to deal with those kind of homework. Okay, here we have X input signals, and also we have the impulse response, and then we have like we need to compute the output, and then we know like the output equal xt convolution with ht, and then since let's talk about actually since based on what we have talked about, we can now use the case one, am I right? Because it not just like a simple impulse sequences. It's just a case two, am I right? So we need to write down the we need to write down the convolution equation and then step by step to calculate the output. But here, for some equations, for someone we have some like tricky way to deal with it. Yeah, for example, yeah, we just let our x1 equal ut, and which means the y1 equal ut like a convolution with ht. Am I right? Yeah. So because this is we just talk about for the same LIT system. Yeah. If our like input is this one and output is this one, am I right? Yeah. So which means if your xt our xt now equal this one, am I right? Because our x1t is ut. So which means x1t minus 3 xt for now is equal x1 minus t minus 3 minus x1 t minus 4. That makes sense to you? Yeah, this is our x1t. Yeah, x1t equal ut, and which means if you replace t minus 3 and you just use replace t minus 3 with using like a 2t, and then you get this one. And if you replace t with t minus 5, and you get this one. That makes sense to you? And which means based on this is a LIT system, we can use some convolution, am I right? So our YT should equal this one. What properties we use here? Yeah, actually it is distributive. Yeah, because you can see if you convolution this one with HT, and then you can easily get this one. That makes sense to you? Yeah. Okay, and then what's this? What properties we can use here? Yeah, actually, it's not like a properties. It's just like a because y1t equal this one, am I right? Which means if our if you use t minus 3 replace t, that makes sense to you, and you can have this one. So your your final equation should equal this one. That makes sense to you? Yeah. Any questions so far? Yeah, you can because you can see here, this is your y1t, am I right? If you use t minus 3 to replace, yeah, because here it's just a x1t minus 3. So this is just a y1t minus 3. And this is just a y1t minus 5. So your yt should equal this one. And then you can easily to represent your yt with y1t minus 3, y1t. Yeah, this is your y1t. Yeah, that makes sense to you? Yeah. Any questions so far? Okay, and let's talk about this, the other one. Yeah, this is our, you can also use, yeah, for the same questions, and you can use the other different method to resolve it. And this is our xt, this is our ht, am I right? So this is our xt. If you draw the figure, am I right? Yeah, and then this is then our yt should equal this one, and you put the since your xt only has a value from 3 to 5, and the value is 1, so you can remove your xt and only like the ht minus 12 left, and then you can see your ht is this one, am I right? So you just put this one here. Yeah, this equation here, and you get this one, am I right? Here, let's talk about this part. Yeah, if we want to remove this part, we need let the t minus tau greater than 0, am I right? So tau should smaller than t, which means we have two different boundary. One is t, the other is 5, am I right? Which means we need to talk about that. If t smaller, greater, smaller equal than 5, and then our upper boundary is what? Is t. Yeah, our boundary should be the smaller one. Okay, and then if we t greater than 5, and then the upper boundary should be 5, because the upper boundary should be the smaller one. So we have this one. That makes sense to you? Yeah, and then you use the equation to resolve it. Okay. Let's talk about the part B. And for the part B, and we have this equation, and the gt equals dxt, like a derivative for xt and convolution with ht. And this is our xt, we know that, and this is ht, yeah. And we also know if you derivative for a unit step function, you can get the delta like a unit impulse function. We talk about it in the previous class. You can review it like in the when we talk about the impulse response and function in chapter 1. Okay, and then we have this. We can easily have this one because you just replace t with t minus t now. Yeah, I'm right. So which means like if we derivative for xt, we can get this equation, am I right? Based on this one. And then since from this equation, we can easily get this equation from to here, am I right? And so which means the gt should equal ht like convolution with yeah, here we use the commutative property, and also after commutative property we use the distributive property. Yeah, just remove the parallels and multiple like each one, and then we use what property? Shifting property. Finally get this one, am I right? That makes sense to you? Yeah, here we have ht, am I right? So we can easily get ht minus 3 and t minus ht minus 5. That makes sense to you? Yeah. Okay, and then let's talk about the part C. The part C is like we have yt, am I right? We have gt, and what's the relationship between gt and yt? Have you ever think this question before? What's the relationship between gt and yt? Yeah, actually you can see the gt is just like the yt after differentiation. You can see here. Yeah, if you notice this one and this one, you can see you just the gt is just yt after differentiated. That makes sense to you? Yeah. So then we have a question: is the differentiation a LIT system? Yeah, you can see. Yes, the answer is yes, it is. Let's talk about that. And you can see if your xt, like after xt, if your xt after differentiation and then convolution with ht, you can get gt. Am I right? Like ht after derivation and convolution with ht, it is gt. And yt is your xt convolution with ht, and then get yt. Am I right? And then which means after you get yt, you differentiation, you get it also get gt. Am I right? So which means the the GT is just a YT after differentiation. You get GT. That make sense to you? Yeah, so which means our GT equal D, like a YT after derivation. Yeah, it is all LIT system. That's a relationship between GT and YT. Yeah. Any questions so far? Yeah, which means you can see this is our YT after derivative. Yeah, after derivative, and you can get this one. Yeah, yeah. Maybe you will have questions. Why here only like the xt will derivative for dt? Why the ht will not? Do you know why? Do you know why? Yeah. Yeah, actually you can see. Actually, we usually like if we deal with a signal, this ht is just an impulse response. It will not change. We usually like a derivative for a system. We just a derivative for the changeable thing. Am I right? Yeah, because the xt here it is not fixed. Am I right? It can be xt can be ax plus b. Also, it can be cx plus c. Also, it can be abx plus z. It can be different. But ht, you can see, what is ht? ht, actually, it is fixed. Why it is fixed? Because you can see the ht, no matter hn or ht, it is just like the delta t goes through the system, which means the ht actually it is fixed if your system is fixed, am I right? But your xt is not. That makes sense to you? Yeah, that's the reason why here, if you derivative for the yt, you just derivative for the xt because xt is changed, but ht never change. No matter if your system is fixed. That makes sense to you? Yeah, which means here I want to talk about one thing here. Here, that's the reason why your y1t equals this one. If you change your t, if you replace t minus 3 here, you just change this t, but now this one, because ht will not change. Am I right? Yeah, so that's the reason why this equation equal y1t minus 3, and this equation equal y1t minus 5. That makes sense to you? Yeah, just remember that. Okay, this is CT convolution DT LIT systems and the CT LIT system. We also talk about for the DT LIT system, like we talk about how to deal with it. For the CT LIT system, we talk about how to deal with it. And you need to finish the homework to practice. Yeah, the practice is very important. And I think we will finish the chapter 2 next week. And then we will have the midterm 2 on next Monday. Yeah, like the March, let me see. March, yeah, March 2nd. Yeah, so we will have midterm 2 on March 2nd. Yeah, like finish homework is very important. And if you have any questions, just let me know. And yeah, we will have new homework for the CT convolution integral. And yeah, doing the homework is very important. Okay, any questions so far? If you don't have any questions, we will finish today's class and see you next week. Okay. Bye.